Huh? Equal. Equality can you know that already. How are you going to do it? Do it by definition. As I said, first do the scratch work. Okay. What will be the scratch work for that? We want this guy and zero's difference to be less than epsilon. The question is, what barrier this n should cross? Because what should be the capital N? Like playing the epsilon and game.
What should be the instant?
Exactly. After that, the difference is going to be smaller than epsilon. Okay? So in order to do that, you just need to solve the inequality, and you have E, which is epsilon, so you can have n to be bigger than epsilon, and take the nth root, so you get pth root, so you get e to the 1 over p. Okay? So if I take this guy plus 1, okay, then I can choose this to be my n. So whenever, so I can then write a proper proof basically after doing the scratch work. So if my n is bigger than or equal to this capital N, then the difference between 1 over n to p and 0 is going to be less than epsilon. Okay? And using basically this result, why we did this result? Because using this result and the algebra of limit properties, you can basically deal with almost all kind of polynomial sequences in the terms of polynomial space. Polynomial sequences are rational sequences with the numerator and denominator as polynomials. Okay. So we need to keep one thing in head. What you are going to learn in this whole of the chapter is not going to be that to know basically definitively or decisively that you take a sequence and you can always tell that whether it is convergent or not convergent. You cannot define divergence. Not convergent. It doesn't satisfy the definition. So there is no answer to this question. You can't tell. There is no single recipe that can work for all sequences actually. So what does this chapter is going to tell you is to basically tell you some of recipes, okay, through which you can basically deal with a large class of sequences and their convergence or divergence, whatever you are interested in. Okay? But it doesn't mean that for all sequences you can always tell that whether they are convergent or divergent. It's a difficult question to answer. So what we are going to learn is to basically some recipes. I can imagine. Imagine I have this space X. I have a set in it, for example, and I'm saying that I have a point, okay, on or inside or outside E, which is kind of a limit point of this this point basically, which is a kind of limit point of this set. Okay? In other words, we say that somehow the set E is getting nearer to the point. Okay? Which is a difficult thing to see intuitively, because we see, at least in this picture, we see E as an static object. It's not moving. Okay? But when I say that a set is approaching towards E, I really mean that there are going to be the points in E to which you can say that they are getting nearer and nearer to P at
The point.
okay. So what I would like to prove basically, the thing that I would like to have is an interesting observation from the theorem, which is theorem 3.2 from Rudin, is that if P is the limit point of a set, okay, so it's like I have a limit point of a set, then I can always find a sequence in that set which is going to converge to that limit point. So in other words, every limit point is kind of a limit of some sequence in that set basically.
अगर बहुत सारे लिमिट पॉइंट रहेंगे सेट के अंदर, तो अगर जितने एक सेट के अंदर बहुत सारे लिमिट पॉइंट हो सकते हैं ना, तो मतलब कितनी सीक्वेंसेस
Exactly. They can be. Okay. So in other words, if E is an inside, say for example, if the point is an inside E, then the answer of this question should be very trivial. Give me a sequence in which every term is in E and it converges to basically, say for example, this point. So if the point is in E, then this question basically is really easy to answer. How many of people understood that what question we are trying to address? We are saying that if, so what I would like to prove is basically part of the theorem. It says that if P is a limit point of E, okay, then there exists a sequence Pn in E. So in other words, all of the terms of the sequence are from E such that Pn converges to E. Pn. Okay. Okay. Now, my point is this. So, for the limit point, there can be two possibilities. So, either it is inside set or it's basically outside set. So, if it is inside set, give me a sequence actually, whose limit is B, okay, and all members of that sequence basically are all terms of the sequence are in inside basically.
Pn is equals to P,
Huh?
constant sequence.
Take a constant sequence basically, because if P is inside E, then there must be at least a constant sequence in which every term is P, it's going to converge to E. So the answer is not interesting when the P is inside E. Okay, the answer is going to be interesting when P is outside E. Okay, okay, not outside, but like okay. Boundary outside. Okay. So I have something like this, which I say that is a limit point of P. Okay. So what we should do?
Why can't we take the boundary?
Then it probably kind of give you an illusion that maybe all boundary points are kind of a. There's difference between a boundary point and a limit point. Okay. They're not two are basically. There is a relation, obviously. You can always find a relationship between quantities, but they are. So we are saying that, because this set E could be closed. In that case, P is going to be inside actually. So we don't want P to be inside E. So imagine that it's somewhere really close to it.
That's it.
That's it. Yeah. That's a P. So what should you do? What do you think that? So in other words, there are a huge number of points here. Just think about that. There are loads of points here. So among these points, I have to cleverly choose some points and make a sequence. And I have to show that those points, through which I have made a sequence, is basically going to converge to that point. So what do you think that what should be?
और कन्वर्ज करे वो उसी भाव में, कन्वर्ज करे उसी भाव में, सेट से ई से आगे
intersection.
Just think about it. For every n, I can draw a ball of radius 1 over n, for example. So I'm drawing a ball of radius 1 over n on P. What is going to be one property? Since P is a limit point, what should be the relationship between this ball and the set?
Intersection.
This should intersect basically. This should intersect. Okay? So the trick is this, that from this intersection, take a point basically, for example, Pn. So I'm saying that take n equal to 1, draw a ball of radius n equal to 1 on P, and take one point basically, any point from that intersection, and call it Q1. And then take n equal to 2, so it's like draw a ball of radius 1/2. Okay? Just like this, think about it. So I take a point. It's a very clever way to do it. Just think about it. So I have a point P here. Okay? So I drawn a ball of, say for example, radius 1, because I took n equal to 1 here. Then I choose a point from here. Okay? And then I'm drawing a ball of radius 1/2, which is going to be smaller. And I'm choosing a point from here. Just think about it. And then I'm drawing another ball, and I'm taking another point from it. So can you see that, somehow these points are going to be
Closer to P.
will get closer and closer and closer.
Sir,
We can make them closer as much as we want. Huh?
P is not in E.
He's not
And
in it.
neither in the boundary.
Yes.
But limit point of E.
But why we are talking about boundary? Why we are talking about boundary? I don't want to hear this word boundary here.
There should be no boundary.
What is boundary? I don't know. Okay. So don't talk.
Don't talk about
Don't
boundary.
talk about boundary. Okay. So we are saying that either P is inside E, so maybe on the line or inside, okay, whatever being online means. So this is something outside,
LOC.
okay? Okay.
Completely outside. Not
It
in.
is completely outside, but it's completely outside and mysteriously in
It's
such
not
a
in the
way.
closure.
Huh?
It's not in the closure of
It should be in the closure better.
Because
If it is a limit point, how can it be in the closure?
Yeah, this was my question.
Yes.
So,
So my point is this, that if this point is a limit point of this, then you draw any ball is going to contain some point, it's going to intersect with the set. So we are saying that if we, for every n, just like formally, I would say the proof is going to be something like that. So I'm just giving you a sketch actually, so, a sketch. Okay? So I'm saying that for every n, and consider ball of radius 1 over n on P. Okay? Now since the P is limit point, since P is limit point, okay, limit point. So this ball is going to intersect with the set E at some point other than P. Okay? Okay?
Sir, why are we taking radius 1?
Okay. I mean, I thought that by seeing the picture you might get some illusion actually that what is going on. But let me draw a bigger picture. Okay. But let's first sort this out and then I'll show you through the picture that why I'm choosing 1 over n. You're gonna see that it's fun to choose 1 over n. You can choose anything else, but do that. Okay, so you have this, alright? Now, if this intersection is non-empty, so there must be some element here. So I'm saying that choose Pn from this intersection. Okay. Choose Pn from this intersection. Okay. Is it making sense? So in other words, for every n I'm choosing, so it's like n equal to 1, I'm choosing P1 from B1 of P intersection E, and I'm choosing P2 from B1 half of P intersection E, and so on and so forth. Okay. So my claim is this. My claim is this, that
So we are excluding P from ball or ball from P.
excluding from ball.
Said the.
Oh, okay. No, okay, forget about that. Alright. It's just a matter of writing. I hope that you are at least that much clever to make sense of it. Anyway, thank you so much. Thanks for this. Okay? So Pn belongs to. So my claim is this, that this Pn that I have chosen is going to converge to P as n goes to infinity. Okay? Should I do it? Okay. Let me draw the picture again. So imagine this is my set P, and the point is here. I guess I'm really close to the set P, but outside. And I'm saying that I'm drawing a ball of radius 1 here. So imagine it's this ball. And from this intersection I'm taking a point. So let's take this point. Okay? Then I'm drawing next ball, which is of the radius 1/2. So that's something like this. Okay? Something like this. And then from this intersection I'm choosing this point. And then a third ball and choosing the point from this one. Can you see what's going on?
Closer to point.
And you choose a fourth ball, and then try to choose a ball from. So you are somehow, these points are kind of getting closer and closer. So that's what basically I want to play. Is it making sense? So the trick behind choosing 1 over n is that this is going to reduce the radius. And this will allow to kind of have an illusion that, okay, that somehow these points are kind of converging.
We are allowed to draw ball on every P because set is open.
On every P, what do you mean by every P?
So we are taking P and 1 off and then.
No, P is a limit point. P is a fixed limit
No,
point.
P1, P2, I mean.
No. All these balls are concentric actually. Okay, so the center is same, so the P is same, which is outside P. So I'm not changing P. Okay, that's one of the thing. So I want to show that Pn converges to P as n goes to infinity. So how can I show it? Okay, so how should I show? How should I begin? So what is the definition of convergence? So the definition of convergence is a game basically, so epsilon n. So someone is going to give me an epsilon. So for a,
Sir, it's not visible.
is it not visible? Okay.
Should
It's fine.
sir, lightning can show.
Okay. So can we open? Do we have more light? That's all we have.
That's all.
That's all we have. So what else can we do? You can say.
Practical कर सकते हैं। लाइट्स ऑफ कर दो। आप सर देखो कुछ नजर आएगा नहीं।
सर यहाँ पे देखिए नीचे बस
Okay. That's right it here.
या
Okay. So for given epsilon positive, so someone has given me epsilon positive, my task is to choose the capital F. Okay? Question is, what should be the capital F and how should I choose it?
स्क्रैच
Scratch word.
P minus
So I want the distance between Pn and P to be less than.
epsilon.
But I know the distance between Pn and P is less than 1 over n. Because from that description, the distance between P and P is less than 1 over n. So I want 1 over n to be smaller than epsilon. So my n should be bigger than what?
1 by epsilon.
Epsilon.
That
So is it making sense? So I mean, if I do scratch work, okay? So my distance between my Pn and the P is smaller than 1 over n. Who can see this? बताओ समझ आ रही है? Why it's smaller than 1 over n? Because Pn belongs to the ball of the radius 1 over n. And what I want basically this guy to be smaller than epsilon. So the question, so what should I choose? So I will say that choose n to be what? Ceiling 1 over epsilon,
Plus 1.
okay, and to be safe side, okay. So if this is the case, then as the distance between Pn and P is smaller than 1 over n, and 1 over n is smaller than, so we can show that this is smaller than epsilon, as we can see it from here actually, for all n bigger than or equal to capital. Okay, so Pn converges to converges to P as it goes to infinity. So that's what we wanted to prove. Okay, making sense? So here is another interpretation of, what do you mean by convergence? So you have a limit and you have a sequence, and somehow the sequence is getting nearer to the point P. Okay, so that's one way to interpret it. The other way to interpret could be that somehow when I'm saying that I have this limit n approaches to infinity, Pn, okay, this is P. This actually means that using Pn, basically I can construct P. Using Pn, I can construct P. What do you mean by that? So in other words, as n will grow, the Pn is going to be approximately equal to this P basically. So in other words, this sequence is going to give you kind of a better approximation of the set.
P.
Obviously there's going to be difference. There is difference. There is always going to be difference between Pn and P. But when we are saying that a sequence is converging to the P, so what basically saying that somehow you can identify P as Pn's, but not all Pn's, but sufficiently big, for sufficiently big in that sense. Okay. So in other words, what we are saying that I can. So in other words, just think about it. Something that you have learned previously. Okay.
So if Pn is convergent.
Just for a moment. So I'm I'm quoting something that you have learned previously. Okay, we haven't proved it, we need to prove it, we will show actually that this is the case. But what does this show actually?
As n goes.
So what does this show? This shows that as n will get bigger and bigger and bigger, this number is going to get closer and closer in its quantity to this irrational set E. Okay? Isn't that something? Okay. Isn't that something which you say very interesting, that on this side you have an irrational number, on this side you have a rational number, and you are saying that they are equal. So we are not saying that they are equal. They can't be equal. Okay, not equal. But we are saying that, so like this guy is approximating your irrational. But when n gets bigger and bigger. Okay. So now let's interpret basically this theorem. What does it say? Just think about it. So this says that if I have a limit point, which is for example outside E, fine, but I can always find a sequence from E which approximates basically your limit point. Just think about it. So though P is not inside E, okay, but still you can approximate it through elements of E. Think about it. You know, isn't E a rational, this irrational number, which we haven't defined yet, we will do it, a limit point for a set of rational numbers?
It is.
It is.
Because
So
all,
you take any neighborhood, it is going to contain always rational numbers. Okay? And that's the evidence basically that from rational numbers I can find a sequence
that converges.
that converges with basically something irrational, which is outside rational number, which is the limit point of E. So in other words, I can use rational numbers to construct not only irrational numbers but all real numbers. So therefore rational numbers are beautiful. The only way that we are able to do mathematics, especially mathematics of real numbers and sequences and all these kind of things on computer is because of, I mean, if you see, because of this result, because of such a result actually. Why? Because just think about it. If you want to tell computer to compute limit at an infinity, you know, how are you going to tell the computer basically that what is infinity?
At least we should define for it.
Can we define infinite? Can we tell basically that computer is, you know, that's what the infinity is? You know, it's almost, because computer is finite actually. So it can only understand things in the terms of finite. So if you can, you know, if you have a clever way to express your infinite things, whatever infinite things are, in the terms of finite things, yes, I can basically now talk about it. So just think about it. You know, E is an irrational number, which is, you know, kind of never going to end. Okay, but I can approximate it through rational numbers. Okay, which can be easily computed by the computer because it has an end actually. Is it making sense?
Sir, it means
you know, for a computer, infinity means some number, which is its limit.
Sir, it means for every real number we have a sequence and rational. That's
exactly. Why? Therefore, that's why we say that rationals are dense enough.
For every real we have sequence and
So
rational.
you take any real number, you can always find a neighborhood. So every real number is a kind of a limit point of for rational numbers. Okay. So what does it mean? It means that you can always find a sequence
Of rationals.
of rational numbers, you know, through which you can approximate whatever your infinity irrationality is. Something beautiful. So it's like, it looks very abstract result, but there's a beautiful meaning behind it.
सर ये थ्योरम हमें बता रहा है कि रियल नंबर्स टोटल के हम कंसीडर कर सकते हैं बाय sequence operation.
No, this result is abstract. We have done it in meter spaces. It's not necessary that it should be true in R. It could be true in even more complicated results. Yes. But as a particular case, if you choose X to be R,
then we can convert.
then we can basically, you can say that. But R result, this result is more powerful.
Yes, sir.
So it's not only talking about R, but it's talking about not only R, but you can talk about Rn, but all kind of meter spaces actually.